Hi, Philip.
Hello, hello, good afternoon to everybody. Hello, welcome to the H-DisNet web conference. I think we are ready to start, Marco, is that correct?
Yes, please.
Okay, very good. Marco is doing the administration of the meeting. First, maybe some technical notes. So all participants have been muted. If you want to say something, you have either to raise the hand, which is a button in the Zoom app, or you just unmute and let us know what you want to say. The intention of the webinar today is that we make you familiar with the thermochemical technology and that we inform you about the outcomes of the EU H2020 project H-DisNet, which has been run from June 2016 until end 2019. And let me give you a short overview of the project. The project has 8 partners. So it's coordinated by KU Leuven, which is a leading partner and takes care of modeling and simulation. And I'm representing KU Leuven here in the meeting. Then we have Watergy as an innovative small medium enterprise from Berlin in Germany. They are taking care of they are specialists in the thermochemical technology, and Martin is representing Watergy in the meeting. Watergy is a spin-off of Technical University of Berlin. TU Berlin is involved also with labs for absorption technology in the project. Next partner is the ZHAW in Switzerland. The energy engineering department is involved, and Serena Danesi is representing that institution in the meeting. The Sir Swan Center from the University of Newcastle is involved in the project. This is a center about energy, merging energy technology and research in general at the University in Newcastle. And Andrew Smallborn is representing that institution in the meeting. Then we have a partner, Rubis from industry, largest copper manufacturer in Europe, and Mukund Bhagwant is representing that partner. Thermaflex is a producer of technology for district networks. Markus Thürnbeck is not able to represent, but I will take over his presentation in the meeting. And we have Alex Accelerant on board. Is a, let's say, innovation enabling company, bring research to market. And Marco is representing, and also Damian is from Accelerant. As the time is quite limited, I would not go through all the partners. I saw a lot of names we had already contact. That's nice to see you again, but we don't have time for to introduce everybody. I would go quickly through the agenda, and then we would start with the meeting. I have control. Yeah, it's working. Very good. First item, so we have blocks. The first block is about introduction. I will give you quick introductions in technology and simulation capabilities we've developed in the project. Then we will see how humidity applications work with the technology. That will include greenhouse applications and automotive applications. Next block is about heating and cooling in buildings with a Berlin demonstrator and with a case study of Hasselt. the next is intelligent and smart applications in networks, so joining networks and using that in the model interconnector case study. And the last block is about market and stakeholder perspectives, how the idea of seeing how the technology could be brought to the market, what the path to the market is. In each block, we have 10 minutes short presentations, and then we have 10 minutes of discussion. And there you are welcome to give us feedback, input, ask questions, whatever is intention. Yeah, we would like to get interaction and to know your opinion about technology. Yeah, then let's start with the introduction of the technology. So, yeah, the question is, what is the potential of the thermochemical technology and how is it able to address the current challenges in energy networks, energy technology, and what is the potential or the benefit that we can get from the technology? So the first thing is that excess heat in industry especially is available at very low temperature, so that the current district heating technology is not able to exploit that. So 50% are probably below the exploitable temperature of current technology. Furthermore, often excess heat is available at long distance from the demand in cities, so 50 kilometers and more, and that needs to be addressed. Then it's not it's a storage issue. I mean, technology or the excess heat is not available at the same time as the demand is, so we need storage capabilities in the network. Return flow temperatures are an issue in existing district networks. So high return flow temperatures are not desired, and thermochemical technology can help to lower return flow temperatures. And the last challenge is that there is the demand density is going down. First, because you want to connect outskirt buildings, and second, because buildings are retrofitted and the heat demand of buildings is going down. If you have near zero energy buildings, then it becomes difficult for networks to operate economically. With that background, we developed the idea of a thermochemical network that is able to utilize low temperature excess heat and to provide services on that base to transport the energy potential of the excess heat to the user. And let me give a quick overview how that technology works. So the basis is a desorption and absorption process at the supply side on the left and the demand side on the right. The excess heat is used to evaporate water from thermochemical fluid, which is basically a salt solution. And that concentrated salt solution is transported through the network to the demand side. And at the demand side, in an absorption process, the heat that was required to concentrate the solution is then again released to provide a service to the environment or to the building or whatever is connected in that situation. And that is 680 kilowatt hours heat per ton of water that is absorbed in that situation. And that is basically the service that can be provided. The idea of the project is that we develop a network with that thermochemical fluid instead of water in the pipes. That is a multi-service network that has space heating by utilizing the heat, cooling by utilizing the drying or the absorption effect and using dry air. We will see that in detail later. We can provide humidity control as an add-on for that technology. And that works quite well with low energy buildings. Furthermore, air quality and comfort can be improved by that kind of service. And then if we have absorption, we can also use that absorption process, removing water from air for drying processes in the industry and enable industrial drying. Furthermore, as mentioned, we have the possibility to utilize very low temperature excess heat for regeneration of the fluid and providing these dimension services in the network. Also for regeneration, we can connect to the return flow of existing networks, utilize the heat there, reduce the return temperature, and provide regeneration, regenerate the fluid to again provide services in the thermochemical network. And all in all, that provides, or the basis is a loss-free transport and storage is possible by means of the thermochemical substance. So if we don't get in contact with humidity, then no losses happen. Let me quickly, maybe you've seen the subtitle of the project, or the whole title of the project, that's Intelligent Hybrid Thermochemical District Networks, and exactly the connection to existing networks and combining the thermochemical transport with the thermal transport. That is where the hybrid in the title refers to. So that is the idea of the project. The overall approach of the project is that we use or developed laboratory devices. New absorber technology was quite important in the project, that we generate performance data from the project, model these performance data, and provide the components or provide the behavior, the performance behavior of the components in simulation models. So for simulation, the Modelica Ideas library was selected as a basis and was extended by an absorber model so that we can include the performance of the absorber in the simulation model, so that it's possible to develop systems, model systems, and simulate systems. And on that basis, we evaluated case studies. We also evaluated demonstrators, and we can design and assess the potential of the technology. So, this slide shows a bit that we are able to model the absorption process. So that is a slide from a validation run with the Switzerland demonstrator, and you see that for the whole range of the operation of the demonstrator from 20 to 33 degrees centigrade, we can predict the temperature and also humidity from 6 to 18 gram water per kilogram. We can predict the behavior. So that's x-axis is measured data in the demonstrator, and y-axis is the predicted performance of the absorber. We use that data in detailed simulation models to predict performance. That's the Modelica-based simulation model of the Berlin demonstrator. And in the end, we use that to evaluate case studies, as we will see later. Yeah, to conclude that block, this is an overview of the network as we have drawn it during the proposal stage, and we will go through that in today's presentation exactly with the blocks. So we have first the humidity control block, which is about heating about greenhouses, humidity control in greenhouses and also in industry. So application of thermochemical technology in that context. Then we have heating and cooling in buildings as the second block after that presentation, after that block here. It's how to apply heating and cooling in the Berlin demonstrator is an important part, and transferring that to building stock in Hasselt. Then we will see the connection with the smart grid with the demonstrator in Newcastle and the Moyle interconnector. And we'll see in the last block how that technology connects to the market, what could be paths to the market and links to the market. We have now a bit time for questions, and then we move on at 14:25 with the greenhouse demonstrator in Switzerland. Are there any questions from the audience?
Yeah, if you have any question, please unmute yourself and you can ask it.
So if there are no questions, I would propose we move on with demonstration from Switzerland. Serena?
Yes, I'm here.
Okay.
So I check if I control the presentation.
I will give you control in a second.
Okay, I don't have at the moment.
Yeah, now it should be fine.
I try?
Yeah.
Yes. So, hi everybody, my name is Serena Danese. I'm from Switzerland, from the Applied University of Zurich of Applied Science. And I want to show you what we did for this project as demonstrator. So we, with our demonstrator, we want to control the humidity and the temperature in a greenhouse. What especially is a commercial greenhouse. You can see here the picture. So we have a quite large room of this greenhouse, and this is the reason that we had to install 9 absorbers. So the absorber in the picture are these gray box. So we have on all the parts, and so we control humidity and temperature. In addition to that, we develop a new system to inject the air in the greenhouse that I'll show you later. And with this system, it is able to save more energy. We ran some tests during the winter, last winter, and during the summer, and we saw, especially for the winter, that we can save a lot of energy. I try to go to the next slide, but okay, here. So this is a picture of one absorber. It was the first absorber that we installed in the greenhouse, and now it's in our lab at the university. You see it's transparent, and the reason is so we can control what happens inside, if there is some dirty, if the distribution of cell solution is good, and so on. On the right, you have a diagram of the system. Actually, it's the system that we have in the lab, but the construction of the absorber is the same. So in the lab, we take the ambient air, and then we have here in this box, we have the possibility to cool or to heat and humidify the air in order to create the condition that we want to test. The air, so then go in this way, so go from the top to the bottom. This is only a problem for the construction in the greenhouse, but the absorption process take place in this colored part. That means the absorption take place in this absorber where the air go from the bottom to the top, and in yellow you can see is the salt solution that go from the top to the bottom. The sand solution then is collected here in a sump and then is pumped around the absorber in this way. How we can control the temperature and the humidity of the air? So we control the temperature of the air through the temperature of the salt solution. We have here an heat exchanger, so we can heat or cool the salt solution depending on the temperature that we want to reach in the air. Oh, sorry. The humidity of the air is controlled through the concentration of the salt solution. So we did manually in the lab, but we can change the concentration of the salt solution in order to reach the required humidity. Of course, so I take the example of absorption. During the absorption, heat is released because the humidity is absorbed, so we have condensation process, and we control the temperature of the air through the heating the salt solution. But we need less heat than without the absorption process, because we use also the latent heat that is released during the absorption to heat the air. And this is the tricks of to save the energy of this technology. If I go to the next slide, so I told you before that we develop a new system to inject the air to the crops in this greenhouse. You can see here a small schema. So we inject the air directly to the crop. So here on this picture is below the table. You see we have this pipe. This pipe has small holes, and through these holes we inject the air. That means we control the temperature not of the entire greenhouse, but we control the temperature only above the crops. In this case, we have two advantages. The first is we don't need, if you see, we don't need to temperate the entire air of the greenhouse, that is, the volume is huge, but we control just the temperature here. That means we need less energy. What is interesting for the greenhouse, for the crops, for the plant, is the temperature around the plant. And the second advantage, you see this is a huge greenhouse. In our demonstrator, it's not the case. We have only flower, the same kind of flower, but actually you can have a type of plant here, a type of here, and another type of here. So different type of plant crops, which maybe require different temperature and humidity. And with this system, so we control the temperature and humidity of each single table. That means we can also create different climate inside the greenhouses. Here I want to show you the results that we did. So we did some tests during the winter and during the summer. Here I show you the test that we had last December 2018. So on the left, we have the relative humidity, and on the right, the temperature. What is interesting, if we have a look to the diagram with the humidity, you see this line is the humidity of the greenhouse. This other line in pink is the humidity at the inlet of our absorber. So you can see that it's already quite different. And the horizontal line are the humidity at the outlet of each absorber. What is very interesting, so you can see that we can maintain the humidity quite constant, so the variation is very small. And also with this system of injecting the air below the table and control the humidity only above the table, you see also which is the huge difference between the humidity that you control if you have a common system in a greenhouse, so you control the air in the greenhouse, and the humidity that we have around the table. So the difference is huge. That means we have to control this one and on of the greenhouse. The same happened with the temperature. So in this day, it was in December, it was quite cold. We have the temperature outside of the greenhouse was more or less 0 degree. And you see here again, the temperature here in that dotted line is the temperature of the greenhouse, and above is the temperature of the outlet of our solver. That means if you want control with the standard system, the temperature of the greenhouse, you have to have a 25 degree, you have to increase this temperature more, and that means at the end you have too high temperature around your crops. But what is interesting is to see the energy that we required. Left is the energy that we require in the greenhouse with the traditional system, and on the right with our traditional system. The traditional system in the greenhouse consists of two different systems with hot water, one below the table and another one above the table. Now we have a look to the light blue and yellow line. Here is the scala. So they are the energy required of the system below the table in blue and above the table in yellow. The experiment was did between 10 o'clock and 4 o'clock. And we see in this day where we didn't have absorber in operation, we need more or less 300 kilowatt hour to maintain a constant temperature. The same we did on the right, where we had the absorber in operation, or the absorber in operation. In any case, we maintain the heating system also in operation to guarantee the 25 degree. But was very interesting. So with the absorber in operation, we need only 50 kilowatt hour. So it was not the same day because it was not possible to do it in the same day, but the outside temperature in both cases was around 0 and 5 degree. So you see that we save quite 70% of the energy to heat the greenhouse. We did also some tests during the summer. Unfortunately, here it's not possible to compare the energy required with our system and with traditional system because there is not a traditional system at the moment. So they don't have the possibility to cool during the summer. What we see here on the left, between 12 o'clock and 8 o'clock, our absorber was in operation. So in blue is the temperature of the greenhouse, and here in red is the temperature at the absorber outlet. So we were able to decrease the temperature more than 10 degrees. On the right, okay, this diagram is not so easy to read, but there are the humidity. I don't have all. So this is the humidity at the inlet of the absorber, and in pink is the humidity at the outlet of the absorber. Unfortunately, this is the absolute humidity, not the relative humidity. Sorry, it's the relative humidity, not the absolute humidity. And so we cannot see, but it was an absorption process. So we remove also in summer a lot of humidity from the greenhouses. This is what happened in summer. You have also here a picture of our table. So the number one is is the air at the outlet of the absorber. So we are here, you can read the temperature, we have more or less 20 degrees, and the humidity. This is a more the humidity air diagram. So before to reach the crops, the air was eaten up from the heat of the greenhouse. But then the crops, so on the table, there was some water, so we have a evaporating cooling effect. So from 1 to 2, so the air is heating up, then we have a cooling down. This effect is the evaporation cooling that is possible only if the air is dried. We did this in our absorber. Then we have from 3 to 4, the transpiration of the plant. And for 4 to 5 it was above in the more or less 2 meters above the plant. So we have also another heating effect. But what we can see that is 5 to 1 is what happened in our absorber. So this 5 to 1 is the effect of our absorber. Then the other depend of the configuration of the greenhouse, of the table, the kind of crop that we have. So the potential of our absorber is quite huge. We see that we go from more or less 40 degrees to 20 degrees. And also we reduce the humidity from 0.014 kilogram per kilogram water per kilogram air to 0.007. So these are a short presentation about what we did in a greenhouse, and I can show you a short video so you can see what we really installed there. So Marco, you can show the video if we have time. So I repeat, the demonstrator was installed in this greenhouse. You see it's a huge greenhouse, and from of this greenhouse we have the part here that is a room with 600 square meters. So we install our demonstrator only in one part of these greenhouses. Here is this room, so you see the table. The table are also particular. We have this special white wall to avoid that cool air fall down before to reach the plant. This is the absorber. So we take the air from these orange ducts. So this is the absorber. The fan is integrated to the construction of absorber. This is the part, it's difficult to see, but this is the pipe of salt solution. So this orange is the valve for the salt solution. And here is the sump where it's integrated the pump for the salt solution. So solution actually see like water. So we have two different sectors in the sump to divide the concentrated salt solution to the diluted salt solution. And this is the special absorber that we install also in the greenhouse. It's design of water G. It's a different design, and we want to compare the two different designs. So of course we have a system, a national instrument system to measure all the temperature and the humidity. You see we measure the humidity direct above the table in order to control the temperature required from the plant. And these are the pipe below the table with this hole. So the air is injected direct on this grid. And this is the absorber in our lab at the university. So we have this transparent absorber. We can monitor everything. And this wood box is to control the air and humidity of the air, the inlet of the absorber. This black is the distribution of the salt solution inside the absorber. We have this fill package in order to distribute really very good the salt solution and to increase the contact surface between the salt solution and the air. And like in the greenhouse, also in the lab, we monitor all the value of temperature, humidity of the air, flow rate of the air, and then flow rate of the salt solution, temperature of the salt solution, the computer. And also we can calculate directly which is the energy go from the salt solution to the air. Okay, this is the video. Thank you very much, Marco. So my presentation is at the end. If you have some question, maybe we...
Yeah, thank you, Serena, for the presentation.
we don't have time.
Yeah, we skip to the next one,
Yes,
because that's
sorry.
related to humidity control, and then we have time for questions.
Okay.
Andrew, are you ready to start to present us?
Yeah,
about
I'm ready.
the automotive humidity control? Yeah, please then move on.
So yeah, thank you, Serena. We will have a few minutes for questions after my talk. I just need to turn over the page to the next slide. So the opportunity that we've been exploring is really around kind of an industrial opportunity for looking at installing H-DisNet technology. We've been working with data from the local automotive manufacturing plant here in Newcastle, which is a very large scale manufacturing of on-road vehicles. And they've kindly provided us with technical data in terms of the way energy is utilized across their site. And in those discussions, we have been able to articulate a good opportunity for the installation of the technology. So in automotive manufacturing, you can see here from this slide here, there are a number of different elements to the manufacturing process. And when you break those down in terms of the way that the energy is utilized, the majority of energy that's utilized in automotive manufacturing process is from the painting system itself. So as you can see from the breakdown on the table there, that can be between 27 and 50% of the overall utilization of energy on such a site. And that's also kind of fits within the context of things like heating, ventilation, and air conditioning. We're going to use as well as compressed air systems as well. So within this framework, there's a lot of excess heat on site, and we wanted to try and use that to facilitate and offset some of the air conditioning costs that are going on site. So the paint shop was where we focused our activity. The paint shop produces a lot of heat, and you can see from that first image there on the left-hand side, there is different ovens that you go through in painting of a vehicle that heat up the surface and cool it down quickly to make sure that the material sets in a nice, efficient way. So you've got, in parallel, lots of heating and then sudden cooling going on. Also within the process, you can see with that big red circle there, there's a process which basically at the end of the painting process, all of the air with all of the volatile chemicals that exist in it, that needs to get burnt in what's called an RTO process, which you use to burn natural gas. And you basically burn all the air as it comes out to burn off these volatile organic chemicals, because these are an environmental challenge. So when you start to break down where does the energy come from across that process, yes, it's coming from the ovens and it's coming from the painting booths. The idea really is to try and get that paint booth to be at the right humidity and temperature to ensure that when the paint sets or dries, it's actually the kind of quality that you want to see on the side of a posh new car. If you get the humidity wrong, you get that kind of image there at the top called checking. And if it's too high, the humidity, you end up with blistering on the surface. So just to give you an impression, an idea there of what it looks like if you get it wrong. So at the particular site that we were interested in looking at, we found that the kind of standard air handling units are unable to deliver the narrow range of temperature and humidity that you might want. So they need to do lots of things like air conditioning and heating in order to maintain a 23 degrees centigrade and a relative humidity of 70 degrees. And you can see that actually the tolerances of those have got to be within 1% and 1 degree. So the challenge is that across different times of the day, you know, particularly where we are, it's obviously lower than 23 degrees most of the time. So we need to find ways of handling that. And of course, this is obviously exacerbated by the fact that these processes are almost working 24 hours a day. So you've got nighttime temperatures and nighttime humidities also to consider. So the H-DisNet installation, the idea is that we take all of the temperatures that we see across the day here and on our analysis, and we need to upgrade those in order to hit the optimal condition for the paint booth. And we would use the liquid desiccant technology in order to achieve that and provide warmer and more humid air. We would use the source of heat from the heat recovery process from the other parts of the paint shop to power that system. And in summary, we found that across different times of the day, we had different heating and cooling demands, but overall, the technical viability of the system seemed viable. To achieve this 23 degrees and 70 humidity, we costed up the system and worked up how much this kind of retrofit solution would cost. And we determined the the return on investment costs for the technology. And we found that that's slightly under 3 years for when you work it all out in all of the detail that you need to for these kinds of analysis. And this savings are really realized through using lower amounts of gas and lower amounts of electricity on site. And then I guess that's my last slide. So we've got a few minutes for questions.
Yeah,
I guess
thank you, Andrew. Thank you very much. Yeah, we have 5 minutes for questions. If you have questions, please raise hand or just unmute and start. Any questions?
Hello, is this working?
Yeah, we can hear you.
Yes, great. So it's a question just to make sure that I understand properly. So if we think about these cases now in the context of a network, to me it looks like, for example, the greenhouse would be at some point in time a consumer of heat, and at some other point in time, for example, in summer, it would be a provider of heat. So am I picturing this correctly, or?
Yes, you are correct. So also the absorber configuration is valid for the both case. Depending which situation we have, the equilibrium between salt solution and air, we can heat or cool down. What we see in this summer, we needed in any case to remove the humidity from the air. That means in the absorber, we wanted to have an absorption process. That means the absorption process release also heat, and we had to cool down the temperature of the salt solution. But in any case, then we have this evaporating cooling on the table. That means at the end, the total energy that we need is always lower than with the traditional system.
Okay.
in the case you need to increase the humidity of the air, you can also use this box, the absorber, this column, to increase the humidity and cool down.
Okay. Thank you.
Welcome.
Further questions? If there are no further questions, then we can move on with the next presentation, with the next block. The next block is about the utilization of the technology for spaces in buildings, for heating and cooling, and also humidity control. And that's the next level of complexity of the system we will see.
Okay, I take over. I'm Martin Buchholz from Watergy in Berlin, and I show a bit about a building demonstrator we have built in Berlin-Adlershof. And we did this together with Technische Universität Berlin, TU Berlin. Marco, can you give me the control?
You should have control now. Yeah.
Yeah, okay. So here you see some pictures. So it's a twin office container we have built just as an office, also used. And you see on the upper picture a facade greenhouse we added. So also in this project we have a greenhouse, but this is not a must. And here a view inside. We have a quite big area. Maybe a fourth of the surface is our experimental area for the system we are using. And we are showing now the applications for the heat supply, but also is used for cooling in the summer. And then always in combination with humidity control, which is an added service for the building, which normally you only have in very expensive systems. And the third thing we look on is we try to have a water recovery from the greenhouse air, and we use this water for evaporative cooling. So our source of cool is the evaporative cooling in combination with heat pumps, as I have to say, for some cases. And then, of course, we're using the desiccant for the drying part of cooling. Here you see the two schemes. On the upper one, you see the heating function, and on the lower one, the cooling function. It's very basic explanation. So in the middle, you see the heat pump we are using. So you see my pointer. So we have the absorbers. You saw the absorber from Switzerland. Here we have a similar element. And the most simple system is just that we have circulating air from the building through the absorber. And what is happening is that we reduce the humidity and convert latent heat into sensible heat. That can be interesting if you have some humidity sources in the building. That can be high attendance of people, can be activities in the kitchen, cooking and so on. Or in special uses, like in a swimming pool or so, of course, you have other humidity sources. And you convert it instead of removing the air to the outside. And this normally is related to ventilation heat losses. And you are, in principle, you can reduce it to zero ventilation heat losses. Of course, then you have also to remove CO2 in the end. And then you also have to aerate again. And then you also need heating. So we add heat from the heat pump to the solution, and we are heating the air with the solution. So this is also our radiator in the building. So it's also the idea of having a cost-effective system where everything is running through one system. And The difference to normal heaters is that we have a direct contact between the liquid desiccant, the thermochemical fluid, as we call it, and the air. This means that also the fluid is a kind of wet filter, removing particles, VOCs, let's say, and of course the humidity from the air. It's also cleaning the air, and by this gives a better quality of air, and also again a reduction of heat losses in the aeration. Then we have a different system where we also add to the absorber the incoming air, the fresh air, and then having a partially open system. Okay, and the second thing we look at is how can we use, besides the internal humidity sources, extra humidity we're producing, and that's similar to the question, to our last question from the audience. So here we can, when we have a sunny day, we can produce latent heat in form of the water vapor in the greenhouse, and with the second absorber, we take up the humidity and convert it within the building, I have to say, to sensible heat. And either this is feeding a storage directly, this heat, or it is using the heat pump as well. And we give the, let's say on a day with low radiation, could be 20 degrees or so, and we give it to the heat pump. We can upgrade it up to 30, 40, 50 degrees, depending on the application. And by this, having a very effective heat pump process in this period when we have some sunlight, and we use it for filling up the storage. And by this, yes, and to have a very efficient heat pump process in that way. And that's the idea of the heating function. In the cooling function during summer, it's a bit different. So we have the second absorber, we use it as an evaporator. So we have not the desiccant fluid here, but normal water. And we use the exhaust air to be humidified and to cool the water. And the cool water is cooling the desiccant cycle. And by this, we can have a kind of natural cooling process. This is a very simplified scheme. For example, we can also use the cool from the air with the heat recovery unit to cool down the incoming air, which is here. And you can also combine it again with the heat pump for more stronger cases on hot summer days. Yes, maybe this slide is only to show here again the two absorber columns and the building. The idea of having humid air as a heat transport facility. So we in these three units you see on the left, we are evaporating water. We already seen the example of the greenhouse where the plants are evaporating the water. You can also imagine like a PV photovoltaic collectors, which is humidified on the backside, by this providing latent heat from such an installation, and the possibility to take the humidity up in the absorber and converting latent heat to sensible heat. And this means the water here on the backside is actively cooling the surface. In summer, it can increase also the electric efficiency of the collector, but in winter, by cooling the surface, we also reduce the heat losses. In theory, we have not done the research on the PV, but on the greenhouse, we can also show that by this we are increasing the collector efficiency by cooling it down and converting to latent heat. The latent heat is not occurring losses, so this is also kind of energy storage from here to the right. And then finally, it's not a must, but of course you have also periods in the winter without sun, then you go to more conventional system using ground heat, and this can be done directly, conventional, but also there are some possibilities to use the same principle and to have also an air cycle through the ground and having evaporation by increasing the heat uptake from the ground to the system. This can be, for example, interesting if you also use the ground heat for cooling in summer and also have some evaporative cooling there. This is maybe a bit more special, but the basic principle maybe is more the solar uptake of. So you see, normally absorption systems are more known for cooling applications and for the drying part of the cooling. And here you can see that we have explored some different means of heating systems, which are quite innovative. I now turn over to also a video, so it's not a professional one. It's just to show you the system on place, and then I finalize with these few slides on the results. Marco, you're already active, I think. Okay, I give over to my voice on the video.
We are here at the H-DisNet demonstrator in Berlin, Adlershof.
We cannot hear. Sorry. You cannot see. Okay. Sorry. Share.
Maybe you have to close the other presentation. Yeah.
Is that working now?
I see the still video.
You see yourself?
Yeah.
Okay.
Demonstrator in Berlin, Adlershof. We try here to demonstrate and to do experiments on thermochemical technology used in buildings. I think this is the main function for heat networks, so it's also important to show that we can provide the services of heating and cooling in buildings with the help of liquid desiccants with the thermochemical fluids. We are here in the building and we have a view into the facade greenhouse from the inside. We use in winter, today is a winter day, outside is around -2 degrees, but the sun is shining, there is a nice temperature in the greenhouse and it's very humid, we have a lot of plants there. And what we are doing is we are using the latent heat of the humid air to get heat, solar heat, and to provide it to the building. And that's what we are doing here inside the absorber. This is the place where our thermochemical fluid is in action. So it's running through these cylinders and it's getting in contact with the greenhouse air. And by this, the hygroscopic property of the desiccant, of this thermochemical fluid, allows us to capture the humidity and by this to change humid air, latent heat, into sensible heat.
We can see how the liquid desiccant is provided to the absorber surface, distribution element.
Here you see one of these columns in action.
The sensible heat is heating the fluid and is getting in contact with the heat exchanger, and then from there we can bring the heat into a thermal storage. So through a few hours of solar radiation in winter days, we can provide heat for the whole day in the building through the heat storage. System, we have two columns with absorber functions, and the first I've just explained is for capturing the heat from the greenhouse. Now the second is our heater in the building, so we can provide heat either by circulating air, so the air from the building goes through the column, is heated by heat from the storage. But also we can control the humidity to a very precise level. The liquid desiccant, our solution, it can dehumidify the air from the building when a lot of people are inside, for example. But when it's very dry here, it's going the other way. It's humidifying the air. You can do this very easily without steam, without spraying water. It's also very hygienic because the salt solution is kind of biological inactive compared to water.
here we are in front of the monitoring and control unit of the machine. We can here control the different actuators, pumps, ventilators and ventil valves, as well as check the temperature levels, humidity levels and flow levels. On the screen on the left hand side we can see more than 50 sensors telling us about the machine state, and on the right hand side more than 30 actuators including valves, pumps and ventilators that are able to drive the heat where it's supposed to be.
Here we are at the regeneration unit of the system. On the very behind you see the residual heat device. So we have some hot air coming from a cooling process, from a machine cooling. Just capture this air which is normally unused and bring it through our desorber. That means we have some heat in the air and it's getting again in contact with our thermochemical fluid. The water in the solution is evaporated and going out through this tube. That means that we are reconcentrating the solution, and this is our energy carrier, and we collect it here in the tank. From here it's pumped back to the building, and vice versa we are getting the diluted solution from the building and use it here in the regeneration unit.
Okay, I think we go now back to this to the presentation, and I show just one day a few results to show the idea. On the left, you see a graph with the temperature. So you see very nicely how the temperature in the greenhouse, the green curve, is going up. The blue one is the ambient temperature, and the red one is the temperature in the building. And the system started, I think, at 9 o'clock or so. And you already see the source of heat in the greenhouse by the temperature. But on the right side, you see this is temperature, the sensable heat plus latent heat, so the enthalpy in the system. So you see that there is even more energy compared to the state of air in the building, and that's what we are using. And next slide, I have again lost my control.
You should have control.
Yeah. Or can you just switch it?
Okay.
The next slide.
Yeah.
So next slide here, very good. We see now the system in the absorber. So on the top we have again the temperature. So the green top is the incoming air from the greenhouse, and the outgoing is the middle curve is just what the difference is, what we bring back to the greenhouse. So the same for the water content in the middle. So this represents the latent heat part, which is just also quite a difference, and then resulting in an energy flow of around 2 kilowatt in maximum in this example. Okay, I think this is more or less my presentation. I don't know if I have time for questions or if you put it to the end.
I will continue, Martin. Thank you, Martin,
Okay.
for giving us insight in the Berlin demonstrator. I have only 3 slides about the transfer of that to Hasselt and to the building stock of Hasselt, and then we have time for question discussion about the use of some technology in buildings. Yeah, I have control. That's working fine. Thank you. Yeah, what we did was basically using the scheme and the technology that has been developed for Berlin and transfer that to the building stock of Hasselt. So we had the question, so what if the technology is applied to selected areas of a city? And we had a close collaboration with the city of Hasselt. They gave us data of 15,000 buildings, demand data, data and building shapes, building geometry. And from these data, we extracted information about typical demand of such average European city, and compared what if we use first the thermochemical system, second conventional gas boilers, third standalone heat pumps, and fourth the conventional district heating system with hot water in the pipes. We have projected a network that covers 155 gigawatt hours per year of the heat demand. That's approximately 42% of the coverage. That was necessary because it's not, you wouldn't apply a network to all the buildings that belong to Hasselt, but more or less the center as you see it here on the right. To carry out that case study, we divided the buildings of the city in 3 clusters, and were clusters with low heat demand, with medium heat demand, and with high heat demand. And so it was easier to develop the system in a way for one building per cluster, and then scale that up for the whole city to represent that and to calculate the pipe diameters and related costs for all the systems. Maybe one important thing is that both the thermochemical system and the district heating system were based on excess heat from industry, run by excess heat from industry by a plant. The case studies included a plant that is 50 kilometers outside the Albert Channel. It's difficult to see here, but there's a channel in north of Hasselt, and that is connected to a plant of Arubis in Olen, and there is a lot of excess heat available, and ship transport of thermochemical fluid to Hasselt was included. The result of that case study was that we have we looked at the CO2 emissions first. There you see that gas boilers, of course, have the highest CO2 emissions. Standalone heat pumps have lower emissions to the COP of that devices. And lowest emissions are the both network system, thermochemical networks, and conventional district heating networks using the excess heat from the plant in Olen. If you look at primary energy, you see approximately the same distribution, high primary energy for boilers and lower energy if you go to the excess utilization. The bit higher CO2 emissions and primary energy use of the thermochemical system is caused by the pumping and the combination with heat pumps to cover peaks in winter, which is difficult by the thermochemical system. If you have a look at the analyzed project costs, we see that the gas boilers and the conventional district heating system is the cheapest solution for Hasselt. That depends, of course, on the excess heat that is available and on the cheap gas, the technology for the gas boilers. And heat pumps are the most expensive solution, and thermochemical systems are in between. With that result, we also went through the countries in Europe and ask ourselves what happens if we go to different locations, different countries, different climate, different market conditions. And I want to draw your attention onto one case, that is Sweden. In Sweden, we have a quite high gas price and relatively low emissions for the electricity. So the electricity power mix has quite low CO2 emissions. And in that situation, the thermochemical system works quite well. It's even cheaper than the gas, the conventional boiler of gas, and that is a thermochemical system. Yeah, that is a transfer to Hasselt case, and the heating and cooling solutions for buildings. And now we have time for questions. Let's say, yeah, it's 5 minutes for questions. Are there any questions for heating and cooling in buildings?
Hi. Just one question regarding temperature levels. Are there any constraints using H-DisNet technology for space heating and domestic hot water preparation?
Maybe we have two dimensions. One is the regeneration process, and this is related to the outside humidity from the ambient air, and which has to take up the water from the fluid. And there, in the winter time, we can work with very low temperatures, like 20 degree to 30 degree, because the outside air is very dry if it's cold. Whilst in the building, we are somehow related to heat pump technology. We think about heating temperatures of 30 degree, 35 degree, 40 degree in this range. So low temperature heat systems are required, and already a quite good building insulation standard. So it's not so good to be used in retrofitting of, or let's say semi renovated buildings or low quality energy efficiency buildings.
Okay, thank you.
Okay, maybe to add to that, especially the low energy, near zero energy buildings are quite interesting candidate, and I mean that's the intention of the EU to develop and to implement these buildings in the building stock. And exactly for these buildings, a quite interesting solution because it's a low temperature system, low exergy system. It has further capabilities of cooling and also including the humidity control.
Mm-hmm.
But not only passive house standard. So if you have very low in energy consumption, of course, the effect you have with this systems is, from the financial point, is also not so interesting anymore. But maybe buildings with 40, 50 kilowatt hours a year per square meter, this could also fit quite well.
Mm-hmm. Okay, and for the domestic hot water production, the system needs to be coupled with another system, or are there any way to produce domestic hot water?
Yes. So of course, this is always a problem with the Legionella. You want to have 60 degrees all the time, but there are also now some innovative solutions working on 40 degree and having a heating of water very close to the user places, and so it goes in the same direction to get to temperatures of 40 degree, or only to use the heat pump, let's say every 2 weeks, to heat up the whole area to 60%, and then work things like that.
Mm-hmm. Mm-hmm. Okay. Thank you.
Are there further questions? If there are no further questions, we are really in time, then we can continue with next presentation block. That presentation block is about the smart grid and power applications. Andrew, are you ready again for giving us insight in that?
I'm ready, yeah. I'm ready to talk.
Good. Yeah, okay.
So, yeah, this section is about, well, I guess, integration with smart grids and power applications. And we're going to talk about two different aspects. One being our what we've called a smart grid demonstrator, which tries to figure out how we might interact with different kinds of networks And then we've got another case study which relates to an interconnector between Scotland and Northern Ireland, which is another kind of waste or excess heat source is utilised in a power generation application. The first thing is that there's a video now, and hopefully that will start as soon as I click here. This one's on YouTube, so you should be able to find it through the H-DisNet website. If I click there, and then it should play, hopefully. Maybe Marco, you could do it.
Okay. Just give me 20 seconds.
The H-DisNet Thermochemical Smart Grid Network demonstrator has recently been established at the Sir Joseph Swan Centre for Energy Research at Newcastle University. The demonstrator aims to determine how a thermochemical network can distribute and use intermittent and low-grade thermal energy. A thermochemical network will be constructed from a network of uninsulated PET pipes. Some will carry a weak liquid desiccant water mixture, shown here in grey. In parallel, a supporting network will carry a strong liquid desiccant water mixture, here shown in green. An energy source, in this case a hot exhaust vent from a bakery, will be used to recover the liquid desiccant. Using an evaporator unit, the weak fluid is heated at relatively low temperatures. In this example, at 60 degrees Celsius. Some of the water carried in the fluid will evaporate, leaving a stronger liquid desiccant water mixture. A network of energy sources can be developed that includes excess heat from industrial sources, solar thermal, district heating systems, electrical transformers, etc. Unlike conventional heat networks, the energy is not stored in the form of increased temperature, which can be lost with time. Instead, it is stored in the strength of the desiccant water mixture, or its thermal chemical potential. As such, network pipes don't need insulation, and the desiccant water mixture can be stored in uninsulated large tanks for later use. The strong liquid desiccant mixture can then be pumped to energy users for air drying, heating, or cooling services. The dehumidification of air to facilitate industrial drying is the simplest application. Here, the strong desiccant water mixture is used together with a dehumidifier unit to dry air for a local indoor swimming pool. The combination of dry air and an evaporative cooler can be used to support air conditioning for the cooling of local buildings and greenhouses. Furthermore, the dehumidification process can be exploited to offer a mild heating and air reconditioning services for local buildings. The H-DisNet system aims to be the first demonstration of a multi-node smart thermochemical network. Within the laboratory, multiple energy sources have been installed, including a combined heat and power unit and a thermophotovoltaic heating system. In addition, a highly controlled electrical heating system has been developed, which can emulate the day-to-day and hour-to-hour thermal outputs of real-world excess heat supplied. A smart thermochemical network comprised of an advanced control system and embedded thermochemical storage is then used to supply energy to different end users.
Right, so that's the end of the video. Garco, can you give me control again of the slides? I've got some slides to sort of summarize some of those aspects.
Yes, I'm on it. You should have control now. Yeah.
So thank you, Mark. So thank you. So as mentioned in the video, and as mentioned kind of a number of times across this webinar, we've had a number of there are a number of places and different ways that actually H-DisNet technology can be applied. It can be utilized across different energy sources and different energy demands. There's some kind of open questions around that. How do you match energy supply and how do you match energy demand? So the next natural question is, how big does storage need to be in order to move energy and keep it within that energy system? And then these different technology sets and sources and sinks of energy, they need to be coupled together. How do they work together? Do they complement each other, and so on? And then final question is really, how does that system, once it's been established, how can that be controlled in a way which means that you don't have any failure of any energy services? So what we wanted to do with our demonstrator was to try to do this by building what is, you can see there, an apparatus there that's been designed and built to be self-contained. So we can test different aspects of those challenges. So we've built this, what we've called a flexible test platform. And what we can do within it is test and create the conditions of multiple thermal energy sources from up to 90 degrees C. And we've also kind of gone the other way, all the way down. I think the lowest we've done is about 30 degrees. Within that system, we can emulate different thermal and air conditioning loads. And within it, we can also store the heat as heat, or we can store it within the thermochemical fluid itself for recovery when we need it or when we want to use it. And we've got embedded within that a number of control systems, and we can measure every aspect of what's going on within the system to measure the performance. And then we can use that to then try out different alternative ways of controlling and testing the system in different ways. Across the apparatus, we've been characterizing some of the components. So we've characterized some PVT systems, that's the thermal aspect added into photovoltaics, thermal collectors, the use of electrical heaters to power the system. And we've been characterizing the inputs, the outputs of those different components and measuring efficiencies. We've also instrumented up our network, as you can see from that complex diagram there in the corner, to measure the different key flow rates, the gas flow rates and so on, so we can measure exactly how well the thing is operating. And we can obviously characterize the temperatures and concentrations and humidity and all of the energy usage across the system. I'll move on to the next slide. Oh, I need to go back one now. Turn back. So our initial testing was what I called 2-node network testing. So this would be a source and a sink. And in this case, we were looking at renewable energy to air conditioning demonstration. So we used our PVT system, and we characterized the PVT system for, well, what was a North UK temperatures and solar irradiance. And we found we could recover from that system about 50 degrees of heat. Obviously, that varies depending on where you are. And we could then use that fluctuating solar energy to then produce local cooling via the H-DisNet technology, 4-degree reduction and a 10% relative humidity in order to sort of demonstrate that we can do some local air conditioning. And we've been measuring that and trying to characterize that system. The next example that we've been working on has been slightly more complex. I would say that this is a 3.5 to 4 node system where we've been using that PVT system with its intermittency and also using electricity to heat the fluid at key times of the day, using what we would just sort of loosely call excess electricity. So off-peak electricity would be used to do heating, and then we can then store the recovered desiccant fluid in storage and then use that in a time-shifted way to produce, in our case, we were looking again at air conditioning. And then the final scenario we've been looking at is emulating excess heat from industry and the return line from a district heating system and coupling those somewhat more regular profiles into storage, and then looking at how we could time shift that to deliver what people wanted as air conditioning, heating or drying, but using demand profiles from different cities across Europe. And I think, from memory, we can just summarize what our demonstrator does. So we've developed a flexible test platform at Newcastle. We can try out different configurations of networks within our test platform, and we were exploring different energy sources and demands to emulate and control them in an effective way. Then next, I'll give a quick summary of what we've done across our work on the Moyle interconnector system. I don't know how many people know much about interconnectors, but an interconnector is an electrical system, and it transfers large amounts of electrical energy across long distances. So a good example here, one of the first ones is what our case study is on, and it's the connection between Scotland and Northern Ireland. And this connection basically takes the AC current seen on either side of that line, and across the sea, it's transferred as direct current. So you have a process where you convert AC to DC. You then transfer that electricity under the sea, effectively on a cable, and then you turn it back to AC on the other side. What's interesting about these connectors is that as we have more and more offshore renewables and we're transferring energy more and more often across the planet, these sorts of systems are becoming very, very, very common. And this system at the time, which was a 500 megawatt system, was one of the smallest. And now it's very small compared to some of the other ones that are going up across the world. But the key thing is that the system is almost identical everywhere you go. And about 1% of the energy is lost in the transfer process, and almost all of that goes to low-grade heat. So whilst the losses to heat are very small, the actual, in terms of percentage terms, they're actually enormous in terms of real-world numbers. So this system is a 500 megawatt system, so there's 500 megawatt system. So 5 megawatts is actually vented heat to atmosphere at around about 40 degrees, that kind of scale. So the question for us in this work was whether or not that energy could be utilized in a more effective way. When you break down the way a system works, The losses are mainly across the transformer and the thyristor valves within the system, and that's where we focused our work. So what you have within the center is you have a stack of thyristors, and they're held within a room, and that room is air conditioned to 15 degrees centigrade, and to keep the humidity as low as possible. The reason to keep humidity low and the reason why it's air conditioned is to prevent corona discharges from one side of the thyristor set to the other side. So what we have to do is we have to maintain, we have to take external air, which is you see a different concentrations of, different humidities and temperatures across the year, and you have to maintain that at 15 degrees within the system. So there's an air conditioning system which delivers that. There's an excess heat sources within the interconnector, as I mentioned before. One source is actually the cooling system for the thyristors. So water is pumped around this thyristor cooling set, and around, about 400 kilowatts per side. So there's two sides, so there's double that. So about 800 kilowatts in total is available at about 40 degrees centigrade. So that's recoverable heat. And then the second source is across the transformer system. There's a cooling system which cools down the transformer, and that again is in between 300 and 378 kilowatts of heat per pole, slightly higher temperature. Obviously, again, a very, very high efficiency process in electrical terms, but actually when you strip it back and you do it at a large enough scale, there's a lot of heat being generated there that can be utilized. And the idea was that we used the heat to drive the desiccant system, and the desiccant system would be then used to offset the air conditioning requirement for the thyristor hall. The calculation was made more complex because the demand on the site, the utilization of the connector varies, and varies in direction over the different years and seasons. But the key is that weather also affects it as well. So we collected data over a number of years and analyzed the amount of available heat from the system, and worked out, actually, is this going to save money for the system? We looked at what we call the case study, which was a retrofit, which was basically just fitting H-DisNet installation around the existing infrastructure. And we also looked at two scenarios of what we're calling new projects, which had slightly different ways of implementing the system, and worked out the payback time for the technology. So the payback times here varied from about 8.7 down to 5 years, and they were all using the savings in electricity in order to justify the payback periods. We also looked at other energy recovery technologies from the site in order to verify and see how effective the solution was compared to things like the organic ranking cycle, etc. But we found that this was actually the most promising in terms of actually delivering something that was actually useful. That's mainly around the fact that utilization temperatures are much lower, and things like organic ranking cycles and other heat recovery systems are not that cost effective at these low temperatures. If you'd like to find out a bit more about this particular piece of work, it's been published in Applied Energy, and the reference is down there at the bottom. It's a much more comprehensive description of what I've just said. And I should now say there's a few more minutes for questions before we move on to the next section.
Yeah, exactly. Thank you, Andrew, for that presentation. 2 presentations. Questions. Are there any questions? Any questions about the smart grid application integration? If there are no questions, then we move on with the last block, which is about market and stakeholders. We have as first presentation Mukund Bhagwat, who's connected from India now. We hope that the connection is working, and he will give us insight in Arubis and the efforts of utilizing excess heat currently with a small perspective for the thermochemical technology. Mukund, are you ready?
Hello, can you hear me?
Yeah, it's working well.
Yes, perfectly.
Yeah.
You should have, yeah, you should have control now.
Okay, I'm starting. It's okay. One moment. One moment, it's working. Yes. And I will make it on presentation. Okay. Good afternoon, everyone. I'm Mukund Bhagwat from Arubis, expert in energy and climate. So what we are saying here is Germany's largest industrial heat project in a city, Hamburg, which has already declared that they want to decrease their CO2 footprint with respect to 1990 by more than 80%. And this is one of the way they are able to achieve it, namely using excess heat from a very large integrated copper producer, which is only 5 kilometers away from the center of the town, but still it is very much active, very environmentally controlled, and at the same time producing excess heat, which is now being used for a new district, namely Haven City East neighborhood, number 1, if you see on the top. That is where already the discussion started for using the heat and providing it about 5 years ago, from 2014 onwards. The project itself was designed, engineered around the same time as we started with developing the H-DisNet technology. Of course, this particular project, which is being shown here on the picture, is using very high temperature heat, so 90 degrees and higher to go in, and what is coming back is 60 degrees. But at the same time, we are aware that after, let's say, the whole high temperature heat is utilized, we still have more than 10 to 15% of all our energy input as low temperature heat. And at this moment, there was no technology available to provide the heat economically and with time shifting, that we are able to give it at the time when people need it. And that's why we started with working with H-DisNet project. So what is behind it? The project scope and complexity are unique and show the potential for the heat change. Essentially, it's a large project. At this moment, we are discussing 3.7 kilometer pipeline using high temperature heat. But essentially, we want to later on go for even higher one. Right now, it is about 8,000 households which are provided with clean heat. I will explain later on why it is clean. And later on, when the project is developed completely, we can even serve 25,000 households. What we are trying to do is, because the heat generated is by burning sulfur as a part of copper production process, there is no carbon dioxide coming out. And essentially, we are saving for 10,000 cars equivalent for a year. And when we are able to extend this heat completely, then we can save even 140,000 tons of CO2 for Hamburg City, if Hamburg City will use it. In addition, within Arubis, we have been able to save a lot of water 12 million cubic meter of cooling of Elba water per year, because if we do not provide this heat to district heating, we have to cool it before we can transfer it to Elba in order not to harm the fish from Elba River. So how does it work? Essentially on the top, you can see the furnace on the left is burning copper ore containing sulfur. Sulfur goes to sulfur dioxide. Sulfur dioxide becomes H2SO4, sulfuric acid, which is used for many chemical things. And that has been captured by extra investment and provided to district heating by a pipeline for which Enercity is the utilizer of this heat in order to provide it to others. This has been already recognized by several awards within Germany, and essentially the head of section, Mr. Thomas Herden, Federal Minister of Energy and Economy, said the external use of industrial heat makes a significant contribution to the city of Hamburg's climate protection goal. And with the help of industrial heat, the emission level in Haven City East falls below the demanding emission threshold for the new development area. What is important is this heat is being developed at high temperature, but with H-DisNet, we have ambition to also use the low temperature heat, and there is a lot of it available. Thank you.
Okay, thank you, Mukund, for that insight and what happening is in Hamburg and what is the potential of first high temperature and then second low temperature heat. The next presentation is from Markus Thürenbeck, who's unfortunately not available because he needs to go to a business trip. He's on a business trip at the moment, not able to connect, but he sent me his notes and I will give that presentation. So Markus Thürenbeck is from Thermoflex, and Thermoflex is producing material for district networks, but also for building technology in buildings, heat distribution technology in buildings. The perspective, oh, I lost the presentation for some reason. One moment, please. Okay. It's again here. Okay, so their perspective is first on producing technology for the district networks and implementing, planning such networks. So they know that quite well. They're also doing water distribution, and that links a bit to the thermochemical technology, because no insulation is required for water distribution. Also for thermochemical fluids, it's not necessary to insulate the pipes. They have a broad perspective on what is happening at the moment in district heating networks. So there are 4 generations now. District heating started with steam in the 80s, 1930. Then it started with the second generation, which used pressurized hot water above 100 degrees centigrade. Now we have the 3rd generation being implemented, or is currently the state of the art. So we have pressurized water below 100 degrees centigrade, and including a lot of sources in that technology. And what is expected as a 4th generation is the integration, intelligent integration of further networks, reduction of temperatures, integration with other systems, with heat pumps mainly, in making such networks kind of more smart. That's a development that is currently much ongoing in the Scandinavian countries and also in Netherlands and so on. So that is a current situation. I asked him to tell what he expects will happen in future. That's the next slide. So they are involved in projects that are doing even lower temperatures, going below 40 or 30 degrees centigrade. That's what they see as fifth generation, using geothermal sources or waste heat. So that's their interest. But that requires underfloor heating of 30 degree in buildings, which we heard already for other systems, or the use of heat pumps to get hot water in the buildings. So even further are going projects with so-called neutral temperature levels. So that means we have really temperature levels of 15 to 20 degree from geothermal temperature or even lower. And then it's really heat pump solutions and local storage that enable us to have the temperature levels that we want to have for buildings. Question is how the thermochemical technology links in there, and what is the perspective in that context. So what is interesting for the district heating is first the benefits of no thermal losses during transport, which means we have no thermal insulation that is required. We have a cheaper network, and we have material lean components in the network, which makes things much simpler. Then we have the possibility of storage, which means that not only transport is, of course, free of losses, but also storage. And we can have a much simpler network management if we have the opportunity of storage. And then we have the add-on of humidity control, so they can offer further services in the network. It's first humidity control you can offer, and second, of course, cooling is also a thing that can happen at the same time with heating with thermochemical technology. We have also barriers that we have to take into account if we think of bringing the technology to the market in that context. First, we have corrosion with the thermochemical fluid, and we have worked a lot of about corrosion in collaboration with Thermoflex. We checked components, first pipes. They produce plastic pipes, so that problem is solved. Then pumps, of course, and these things. But we discovered that there are solutions for all of these aspects, and it's possible to transport a corrosive fluid in a pipe network. Then next barrier is the exchange of the technology that is required. So it's really a new technology for the network and for demand and supply side. So that requires exchanging things, and that has to be taken into account. And a third barrier from Thermoflex perspective is the technology readiness level, which is at the moment at about 4 to 6. That's what we are developing. And there are some steps to go in pilot projects or whatever to implement the technology at the market. Yeah, that is the perspective of Thermoflex. I hope I presented correctly. And we have one short last presentation here in that block from Accelerment about the stakeholder perspectives and especially addressing various benefits, potentials, and possibilities. Damien, are you ready to present?
Okay, can you hear me?
Yeah, I can hear.
Okay, perfect. Yeah. My name is Damian Berli. Me and my partners at Accelerment support the H-DisNet project with regard to exploitation since 2018. And Marco, could you please go one slide ahead? In the next step, I will introduce the perspective of stakeholders quickly. What you see on the slide is the result of a stakeholder mapping, which was conducted by the consortium as part of the exploitation activities. Key stakeholders were divided into 3 main groups. The first group was characterized as energy supply. Key stakeholders here are especially manufacturers providing waste heat, as well as intermediates such as district heating operators. The second group was characterized as energy demand. It consists of various stakeholders such as private and public buildings, larger communities such as cities, as well as industrial sites. The third group finally was characterized as various supporting areas, ranging from policy to economic and technological aspects. In order to complement the already existing knowledge in the consortium, we conducted several interviews in the course of the summer, focusing especially on supply and demand side perspectives. The main objective was the identification of challenges and opportunities related to the exploitation of two of the project's most important or most promising applications, industrial drying and humidity control in buildings. These applications were selected due to their positive financial and also ecological prospects. More specifically, the H-DisNet technology has the potential to reduce fuel consumption for drying by 85%. In addition, it could serve as an affordable, energy-efficient solution for humidity control in buildings. The results, could you please go one slide ahead? The results of the interviews are depicted here on the slide. Basically, most of the participants were interested in the potential of the technology. With regard to the specific stakeholder groups, we found varying interests or varying highlights. Participants and experts in the field of district heating argued that the sector was quite traditional and thus slow in adapting to new technologies. To progress in this area, they recommended the targeting of small-scale networks, since these would involve lower risk and also a lower investment. The second group of industrial stakeholders, on the other hand, were especially interested in the possible use of low-temperature waste heat. However, they characterized the current technology readiness level as a key barrier for market exploitation. So consequently, they recommended to conduct further pilot projects in order to generate additional data on the technology. Participants from the building sector finally highlighted the increasing demand for energy-efficient humidity control in private as well as public buildings. It was recommended to focus on niche markets, for example, such as clean rooms. In a second step, it would also be imaginable to have a small, affordable solution for the mass market, which had to be developed. They further highlighted that such a development should also be aligned with manufacturers of ventilation systems and heat pumps. So in conclusion, the perspective of stakeholders regarding the potential of the technology is mostly positive. However, as one of the typical drawbacks, especially the technology readiness is a key barrier to the market, which the consortium is trying to address by the introduction of pilot projects. That's it from my side.
Okay, thank you, Damian, for that overview of the stakeholder analysis within the project. That is one perspective of stakeholders. The stakeholders have responded to our survey. I would like to, I mean, you've seen the technology today, you've seen modeling simulation, the application in the demonstrators and in the case studies. And we are currently looking how we can implement the technology in future. And we would like to get your comments to that, if you, how we think that could be approached, where you see the potential, maybe adding more perspectives to the stakeholders that we have seen at the moment. So please give us your feedback. Are there any comments for the future of the technology, where it could go, what is the right direction to develop that, or any ideas, any opportunities you see?
I have one question actually regarding the heat recovery that Aurubis has done in Hafen City.
Yes, please go ahead.
I wanted to ask you at which stage of the copper production process, you have implemented the heat recovery thanks to the thermochemical technology?
Yes, thank you for the question. Can you hear me?
Yeah, I can hear you perfectly. Thank you.
Okay, so thank you for the question. As I explained, at this moment, the heat recovery is at high temperature. In the first place, we recovered the heat at maybe even 400 degrees, 200 degrees, convert it to electricity. Then whatever is remaining, we are, let's say, managing it at 90 degrees and providing it to the district heating network, and it is coming back at 60 degrees centigrade, which we are again heating using the excess heat which is available at higher temperature. But in all that process, we have a lot of exhaust heat going out from furnaces, etc. And it is that heat in the building, which is also about another 10%. So to give you an idea, we have something like 1 terawatt hour of electricity and 1.5 terawatt hours of gas-based energy input. In addition to that, we have this chemical heat coming from sulfur, burning of sulfur. So there is a lot of heat available. In fact, all the internal needs are fulfilled. That's why we are supplying it to district heating, but we still have a lot of heat available. So if we can have this technology perfected on a industrial scale from this hybrid network, thermochemical network, then we can supply even the larger region using this excess heat. I don't know if it answers your question.
Yeah. That was clear.
Okay, thank you. Just to continue, there is, according to a European study, there is a potential for excess heat at low temperature, which can cover almost all of the air heating need of the buildings. Let's say 10 years from now, provided the buildings are insulated, etc., so that there is no further loss of heat due to the building stock. But as mentioned earlier by partners, when the buildings are already, let's say, energy efficient, then low temperature heat makes it even more efficient by not losing any energy during the heat transfer, because it's a chemical energy and it is not, it does not require any insulation.
Yeah.
Yeah, it was one, maybe to add to that, it was one conclusion from the Hasselt case study that we saw for local solutions that you can connect with a thermal district network, as it is done here in Hamburg. That is the most efficient solution. But if it comes to longer transport, maybe to the outskirts of the city or to low demand areas, then it makes sense also to include the thermochemical technology with its potentials.
I think it's important to see, you can see a lot of water going there. So normally we can load our inland barges with thermochemical solution and transport it to 50 kilometers and then take that heat, the chemical heat, for, as mentioned by Philip, for other less dense area which are still connected with the inland waterways.
Yeah, that's interesting from the perspective of a district heating operator, I guess, and this should be something that I hope it will be further developed within the project or future projects related to thermochemical technology.
Oh, that is very good feedback. Thank you.
Another point is the possibility to store this thermochemical liquid also for a long time without losses. I mean, in comparison with hot water, so we need once less volume because the energy density is higher, and we don't need to isolate, so we don't have to take account on losses.
Okay, thank you.
welcome. Further questions or comments or whatever?
I think, Philip, if I may, Mukund here, it will be interesting if anybody is interested to form a new consortium for the further stage of this project. Please inform your interest to Philip so that we can take it further.
Yeah, definitely welcome. Yeah. If there are any ideas of developing, applying that, I mean, we are looking for pilots, we call it, so that we bring that from the demonstrator level to a real environment, applications, and develop the technology in these environments in the end to the market readiness.
The reason why we are saying it is I follow quite well the regulatory discussion in Brussels. And right now, this European Green Deal, which is coming up, is requesting very high decarbonization in all the member states. And there will be a review of all these national energy climate plans, particularly for heating and cooling, once they have submitted their proposals. And this is the technology which will be ready, we think, in 5 to 10 years from now, but which will give solution at the right time when those member states who are lacking today in energy efficient housing, we will be ready to help them further to decrease it to zero.
Yeah. And from the perspective of the technology itself, all the applications that involve humidity control, drying, and all these kind of controlling humidity in air, that is interesting because the technology provides that that service automatically. And these services are usually developed in competing technology. They are developed with high energy effort or with other problems of hygienic problems and these things in buildings. So that's quite interesting to develop further implementation projects on that basis.
Just one question.
Yeah, please.
When I don't know what is the timeline now of the project, when it's going to end, H-DisNet, and if you are planning already a new proposal for next years, or what is the timeline that you have in mind now, and also for the
yep
next step?
H-DisNet is ending in December, end of December this year. And there are several small proposals under development, but we are also interested in larger collaborative projects again at EU level. So that is, we are looking for opportunities at the moment.
Mm-hmm. Mm-hmm. Okay.
Are there any further comments, questions, suggestions? If not, then let me thank all the participants for joining the H-DisNet webinar. Furthermore, I would like to thank all the partners for contributing, first to the project and second to the webinar today. And I would like to thank also Marco for managing all the technology in the background so well. I think that worked quite well. Yeah, and let's stay in contact, and I wish you a nice day. Okay, thank you for joining. Bye-bye.
Thank you very much.
Thank you.
Bye-bye, everybody. It was a pleasure.
Thank you.
Thank you.